So let's solve part A again. We'll call this AII using energy conservation. So here I've drawn the picture again, just real quick. And what is the key to energy conservation? The key to energy conservation is identifying an initial and final position and then comparing the energies of the two. So if energy is conserved, in other words, there's no friction, then the initial energy equals the final energy. If there is friction, then we would say that the total work done by the non-conservative force, or the work done by friction, is equal to the change in mechanical energy. Where mechanical energy, remember, is Ke plus potential energy. Where now kinetic energy is 1/2 mv squared, but potential energy could be the potential energy due to gravity, or the potential energy due to springs, or the potential energy due to pressure, any kind of potential energy that you can come up with. So that's your mechanical energy, which only changes if there's non-conservative forces. So let's just go ahead and just solve this problem by writing EI equals EF, energy at the top equals energy at the bottom, and that's the kinetic energy at the top plus potential energy at the top equals kinetic energy at the bottom plus potential energy at the bottom. And let's just fill in 1/2 mv initial squared plus mgh initial plus 1/2 equals 1/2 mv final squared plus mgh final, and just plug in what we know and what we don't know. The initial velocity is 0. The initial height is ht. Whoops. The initial velocity is 0. Initial height is ht. And the final velocity is what we're looking for. And the final height is hs. So now we just solve for the final velocity. And we get the final velocity is the square root of 2g times the change in height, ht minus hs. Pretty straightforward. Seems like a lot less work than the other problem. Just to notice that, like, when would you use, than the other method. When would you use energy conservation versus Newton's second law? And rule of thumb is basically, since energy conservation comes from the work energy theorem, right? The work energy theorem is work total equals change in kinetic energy. I think this is work total, yeah. And work total, whoops, I'm trying to, oh, never mind, I won't explain what I'm trying to do. Work total, stop it. Is something like, it's not equal to F delta X. Work total is actually F net dot ds, but it's like a force times a distance. Kinetic energy is like 1/2 mv squared. So if we're trying to relate positions to velocities, then usually work energy or energy conservation is the way to go. If you're trying to relate things to accelerations, that's usually when you're using Newton's second law instead. Newton's second law and kinematics instead. Last part of this problem is part B, which is how far is the spring going to be compressed. And again, we want to decide how to do this problem. Well, I think hopefully it's clearly should be an energy conservation problem, and here's why. Because Newton's second law is generally, let me just say before I get there, what we're looking at here is the spring when the mass hits the spring, right? That's the position. I'm showing the position where it's just before it hits the spring, when it has that final velocity that we calculated. When the mass hits the spring then compresses a distance delta x. But when it compresses a distance delta x, the acceleration is not constant. Actually, the acceleration isn't constant, right? It's g sine theta until it hits the spring. Then the acceleration changes, and even then, the acceleration changes while it's moving the spring, because the force is dependent on the force that the spring exerts. The spring force is dependent on the compression of the spring, right? F equals minus kx. So the acceleration is not constant. So we generally don't solve Newton's second law problems when the acceleration is not constant. So this is an energy problem, which we can do when acceleration is constant. EI equals EF. And the question is which positions are we going to choose? We have 3 positions. And I would just choose the top of the ramp and the lowest point, right? So we ignore that point right where it hits the spring that we've been calculating the velocity for. And we can write down the energy, the mechanical energy, 1/2 mv squared plus mgh, and now we've got a spring potential energy 1/2 kx squared in there. Initially, the spring is not compressed at the top of the ramp. It's not even touching the spring. I just included in there for completeness. X initial is going to be 0. But then when it gets to the bottom of the ramp, the bottom of the spring, when it's fully compressed, so we're talking about the final position here. Sorry, I'm having a little trouble. Okay, we have the spring will be compressed a distance to a position xf, or a distance delta x. Let's go ahead and fill in what we know and what we don't know. The initial kinetic energy is 0 because it starts at rest. The final kinetic energy is 0 because it stops at the end. We're not talking about that intermediate position. And the initial height is h at the top, ht. The initial compression of the spring is 0. And at the bottom, at the very bottom, right, when it is fully compressed, it's not at hs. It's at some lower position than hs. If the spring is compressed by a distance delta x, then it's gone down an additional delta h, right? It's gone down an additional delta h. So the distance that it has, the position, the vertical position is now hs minus delta h, where delta h is delta x sine theta. And the compression, where delta x is the compression of the spring, and for whatever reason, I used both xf and delta x, but they're the same thing. Xf was the final position, therefore the compression is delta x. Those are the same thing. Okay, so we can go ahead and just, what did I do there? Don't know what I did there. I rewrote the same equation. I just wrote it, I don't know why I wrote it again. So now it's simply, we know everything in this equation as long as we make the substitution delta h equals delta x sine theta, and we can solve for delta x. But what you should notice is that this is a quadratic equation, that there's a delta x and a delta x squared, and so you'd have to use the quadratic equation to solve it. Okay. Now, it might be a slightly easier way to think about this problem, and that is to use the two positions down at the bottom of the ramp instead of the position at the top of the ramp, or the position at the bottom of the ramp. If we use the two positions down at the bottom of the ramp, and we can really just another way to look at it, we can say that the total work done on the block once it hits the spring is going to be its change in kinetic energy. But notice that the total work done is both the work done by gravity, because it's still moving down in the gravitational field, plus the work done by the spring equals change in kinetic energy. Just, I think it's a little easier to get this conceptually, where the work done by gravity is mg delta h, that delta h that we calculated on the previous page, and the work done by the spring is 1/2 k delta x squared. And the change in kinetic energy, now we're talking about the change in kinetic energy from when it had its maximum velocity, which we calculated previously as being 2g ht minus hs. So as long as so there's really nothing new. There is nothing new here. We make those substitutions for delta h and v final, and we still have a quadratic equation delta x that we can solve for delta x. Okay, so that's just solving. Whoops, sorry, I'm getting ahead of myself here. That's solving part B using energy conservation and work energy.